All right, chemistry, let's take a look at our video lecture for section 3 in chapter 7. We're going to talk about using chemical formulas. The last two sections, we spent a lot of time figuring out how to make chemical formulas. Now let's figure out how we can use them. After this video lecture, I want you to be able to calculate the formula mass or molar mass of any given compound. And you should be able to give that compound's name or formula and then get to this mass. Then use that molar mass to convert between mass in grams and amount in moles of a compound. Uh-oh, guys, here comes the math. Conversions are back. Calculate the number of molecules, formula units, or ions in a given molar amount of a chemical compound. Then lastly, calculate the percentage composition of a given chemical compound. So we know that a chemical formula indicates the elements present in a compound and the relative number of atoms or ions of each element present in that compound. We already know this. Chemical formulas also allow chemists to calculate the number of other characteristic values of a compound, and this is where we're going to take one step further. We can take a chemical formula and calculate formula mass, molar mass, or percentage composition. Let's start with formula masses. The formula mass of any molecule, formula unit, or ion is the sum of the average atomic masses of all atoms represented in its formula. For example, if we try to calculate the formula mass for water, which is H2O, we know that the average atomic mass of hydrogen is 1.1 AMU, and the average atomic mass of oxygen is 16.00 AMU. How do you know this? Because you looked at the periodic table. Now, if I'm going to try to calculate the mass, the formula mass of water, I need to take into account that there are two hydrogen atoms. And so I'll simply take two hydrogen atoms, convert out of atoms into AMU using a conversion factor in the exact same way I've done in past chapters. This will allow me to have the atoms of hydrogen cancel, leaving only AMU. Simple multiplication and division will let you know that this is 2.02 AMU from the hydrogens. And there's only one oxygen atom, and I can convert that using the mass of oxygen from the periodic table to figure out that the mass due to oxygen is 16.00 AMU. Add those together, you get the average mass of a water molecule being 18.02 AMU. Now, the mass of a water molecule can be referred to as its molecular mass, the mass of a molecule. The mass of one formula unit of an ionic compound, right, because ionic compounds are not molecules. For example, NaCl is not a molecular mass. The mass of any unit represented by a chemical formula, H2O or NaCl, can be referred to as the formula mass, right? So we need to make sure that we are paying attention to whether or not we're talking about molecules or formula units, because we cannot call the mass of a formula unit the molecular mass because it's not a molecule.
Like individual atoms, molecules and ions also have a characteristic average mass. To find this mass, we add the average masses of the atoms making up the compound. In a molecule of water, there are two atoms of hydrogen, so we multiply the atomic mass of hydrogen by 2. There is also one atom of oxygen, so we multiply the atomic mass of oxygen by 1. We then add these masses to find the average atomic mass of the whole molecule.
Let's try a sample problem. I'm going to show you how to find the formula mass for potassium chlorate, KClO3. Now, the mass of the formula unit of KClO3 is found by adding the masses of one potassium atom, one chlorine atom, and 3 oxygen atoms. Atomic masses can be found in the periodic table in the back of your book, or the one that I've given to you, or if you need to get a new one, get a new one. In your calculations, it's going to be easiest if you simply round the atomic masses to 2 decimal places, just so you guys don't get overwhelmed by numbers. So first, I'm going to convert the mass of I'm going to convert one potassium atom into mass using the using the average atomic mass of potassium found on the periodic table. so that potassium atoms cancel, leaving only the unit of AMU. Do the same thing with chlorine, and then my 3 oxygen atoms, right? And I get 39.10 AMU due to the potassium, 35.45 AMU due to the chlorine, and then 48.00 AMU due to the 3 oxygen atoms. Simply add those 3 numbers, and I find that the formula mass for potassium chlorate is 122.55 AMU.
A mole is a quantity, similar to a dozen. There are 12 items in a dozen, and 6.022 times 10 to the 23rd items in a mole. A dozen eggs, a dozen bagels, and a dozen pencils have different weights or masses and have different properties. The term dozen tells you that there are 12 of the item. Similarly, a mole of iron and a mole of copper have different masses and have different properties, but both represent the same number of atoms, 6.022 times 10 to the 23rd atoms.
So we just covered formula masses. Now let's talk about molar masses. They're going to be constructed and thought of in a very, very similar way, but the unit is going to be different. And that's very, very critical here. We have to pay attention to units. So the molar mass of a substance is something we've already covered. It's equal to the mass in grams of 1 mole, or approximately 6.022 times 10 to the 23rd particles of a substance. For example, the molar mass of pure calcium, meaning nothing but calcium, is 40.08 grams per mole, because 1 mole of calcium atoms has a mass of 40.08 grams. And so we say 40.08 grams per mole, as in per 1 mole. The molar mass of a compound is calculated by adding the masses of the elements present in a mole of that molecule or formula unit that makes up that compound. 1 mole of water molecules contains exactly 2 moles of hydrogen atoms and 1 mole of oxygen atoms. The molar mass of water is calculated as follows, and I hope you notice something very, very familiar. I convert my 2 moles of hydrogen into grams by using the molar mass of hydrogen, making sure that the moles of my molar mass are on the denominator so that the moles of hydrogen cancel, leaving only mass because I'm calculating a molar mass. And do the same thing for oxygen, making sure that the moles of oxygen cancel, leaving only grams of oxygen in my answer. And so adding those 2 numbers, 2.02 grams of hydrogen and 16.00 grams of oxygen, I find that the molar mass of the water molecule is 18.02 grams per mole. Did you notice that a compound's molar mass is numerically equal to its formula mass? Yes, 1 molecule of water has a mass, a molecular mass of 18.02 AMU. But a mole of water has a mass of 18.02 grams. I'm hoping you see the difference in units and can conceptualize that difference.
Elements can have more than one stable isotope. Helium has 2 stable isotopes, helium-3 and helium-4. Naturally abundant elements have a variety of stable isotopes. Copper is made up of the stable isotopes copper-63 and copper-65. To find the average atomic mass of an element, multiply the mole fraction times the atomic mass for each naturally occurring stable isotope of that element. For example, naturally occurring copper is 69% copper-63 and 31% copper-65. Multiplying these fractions times their respective atomic masses yields the average atomic mass of copper at 63.6 grams per mole.
So here are some examples. Please refer to this as we work on our quick write, as we work on our assignments and any practice problems here. If you're going to calculate the molar masses for ionic compounds, remember that's going to be a formula unit. Here's our examples. We have zinc chloride, we have zinc sulfate, and we have ammonium sulfate, right? The exact same steps are being shown here using calculating for 2 elements, then 3 elements, and then 4 elements. And you'll see that it's carried out the exact same way each time. But let's work through one very, very specifically. What is the molar mass of barium nitrate? So 1 mole of barium nitrate contains 1 mole of barium, 2 moles of nitrogen, and 6 moles of oxygen. So first I'm going to convert 1 mole of barium into grams of barium using the molar mass of barium from where? The periodic table. Cancel out moles of barium to reveal 137.33 grams of barium. Then convert my 2 moles of nitrogen into grams of nitrogen using the molar mass of nitrogen to give 28.02 grams of nitrogen. Remember, the moles have to cancel. And then lastly, my 6 moles of oxygen into 96.00 grams of oxygen. Please make sure that the moles cancel. Show your work or I will not give you credit because you are not putting yourself in a position to be successful later. You have to show your work. You have to learn this system. And we reveal that the molar mass of barium nitrate is 261.35 grams per mole. And we can use molar mass as a conversion factor, which is going to be critical for us moving forward. The molar mass of a compound can be used as a conversion factor to relate an amount in moles to mass in grams for a given substance. That means to convert between them. To convert between moles and grams, multiply the amount of moles by the molar mass. As simple as that. Again, here's a diagram that is included for your convenience. If you are trying to convert from mass in grams into the amount of moles, we use a particular setup of conversion factor. We can also use Avogadro's number to convert from moles into the number of molecules of a particular molecule or formula unit. We can also go in the other direction, right? But we have to get back into the habit of using conversion factors and showing our work. Again, please refer to this diagram anytime you're starting a conversion so that you can be headed in the right direction.
The mass of a compound and the amount in moles are related by the molar mass. To convert from mass in grams to amount in moles, multiply by 1 over the molar mass of the compound. For example, to find the number of moles of water in 25.05 grams of water, we multiply by 1 over the molar mass of water, 18.01 grams per mole. We see that the units cancel to give us moles. In 25.05 grams of water, there are 1.391 moles. To convert from amount in moles to mass in grams, multiply by the molar mass of the compound. For example, to find the number of grams of water in 2 moles of water, we multiply by the molar mass of water. We see that the units cancel to give us grams. 2 moles of water have a mass of 36.02 grams.
So let's work through a sample problem. What is the mass in grams of 2.5 moles of oxygen gas? Now remember, this is oxygen gas, so it's going to be O2, not just O. So we've identified that we have 2.50 moles of O2. Our unknown, which is what we want to convert into, is mass of O2. So we're going from moles of O2 into grams of O2. So that should communicate to you right off the bat that we are going to be, whoa, did I skip? Whoa. That we are going to be having to convert out of moles and into grams, okay? That's going to tell you that you're going to construct your conversion factor a very specific way, with moles on the bottom and grams on the top. So as we go to calculate that mass of molar mass of O2, because that's what we have to use as a conversion factor, we need to make sure that it is correct. We have 2 moles of oxygen, right? It's O2. So 2 moles of oxygen multiplied by the molar mass of oxygen by itself, we get 32 grams. And so we use that molar mass of O2 to convert from moles into mass, putting that mole of O2 on the bottom, grams of O2 on the top, so that moles will cancel, leaving only grams. And the last thing to do, the very last thing to do, is multiply. Again, this is very, very system-based. If we want to convert between number of moles and number of particles, for example, we can do that simply using Avogadro's number in the way that we've already done this year, right? Simply match up the units that have to cancel and let that inform where you should place your actual values. So let's try another one. Ibuprofen, C13H18O2, is the active ingredient in many non-prescription pain relievers, and its molar mass is 206.31 grams per mole. Got a few questions for you. If the tablets in a bottle contain a total of 33 grams of ibuprofen, how many moles of ibuprofen are in the bottle? Then, how many molecules of ibuprofen are in the bottle? And lastly, what is the total mass in grams of only carbon, just the carbon that's there, in 33 grams of ibuprofen? So, let's start with the first question. In 33 grams of ibuprofen, it has a molar mass of 206.31 grams per mole. What is the number of moles of ibuprofen? How many molecules of ibuprofen are present? Then we need the total mass of only carbon. So, the first thing I'm going to do is understand what I'm converting out of and what I'm converting into. And so I know in my general setup, I'm going to start with grams of ibuprofen. And then I can use the molar mass of ibuprofen, which is given to me by the problem, to convert out of grams and into moles, because moles of ibuprofen is the first thing I'm being asked for. Notice that in this example, this is the first example where I've had grams of ibuprofen on the denominator of my conversion factor and moles of ibuprofen on the numerator. Why is this so? Because I need to cancel the grams, because that's what grams were given to me as a unit, and I need to convert out of grams and into moles. And so this is my general setup right here as I go from grams to moles. Next up, for B, I am going to convert from moles into the number of molecules, right? Because that's what B is asking me for. And so once I know the number of molecules, and notice I haven't plugged any of those values that were given to me by the problem in here yet. Once I know the number of molecules of ibuprofen, I can use Avogadro's number as a conversion factor to convert into molecules. Notice here, moles are on the denominator because I need the moles to cancel to leave only molecules as the unit. And lastly, for C, I'm going to convert out of moles of ibuprofen and into moles of carbon by itself, only carbon by itself. So I can use the molar mass of carbon to convert into grams of carbon. Okay? Notice that I'm converting out of moles of ibuprofen into moles of carbon, and then my second conversion factor is allowing me to convert out of moles of carbon and into grams of carbon. So let's take a look at this with all the numbers plugged in. The problem says that I have 33 grams of ibuprofen, so I simply plug that in at the beginning, convert out of grams into moles, and I have 0.16 moles of ibuprofen. I take that 0.16 moles of ibuprofen and plug that into the start of B using Avogadro's number to convert out of moles and into molecules, and I find that I have 9.6 times 10 to the 22nd molecules of ibuprofen. I'm still using that moles of ibuprofen I got in step A, the 0.16 moles of ibuprofen, to convert out of moles of ibuprofen into moles of carbon, and then the molar mass of carbon to convert into grams of carbon. Now, a lot of people get intimidated by percent composition, which will be the last thing that we cover in this section. However, it blows my mind because percent composition is very, very easy to calculate, and especially because you already know what a percent is. It is often useful to know the percentage by mass of a particular element in a chemical compound. To find the mass percentage of an element in a compound, the following equation can be used. The mass of an element in the sample, the mass of the element in the sample of that compound divided by the mass of the sample, the whole sample, right? The mass of a specific element divided by the mass of the sample, and then you multiply by 100 to get that into a percentage. The mass percentage of an element in a compound is the same regardless of the sample size. So it doesn't matter if I give you 10 grams of it, 100 grams of it, or 1,000 grams of it, the mass percentage will always be the same. The percentage of an element in a compound can be calculated by determining how many grams of the element are present in 1 mole of the compound. So we take the mass of that element in 1 mole of the compound. We divide it by the molar mass of that compound and then multiply by 100 to get it into a percentage. The percentage by mass of each element in a compound is known as the percentage composition of that compound. Let's take a look at it graphically. We have a couple of different iron oxides because iron, remember, can form a +3 charge or a +2 charge, and so it's going to take a different number of irons and a different number of oxygens in each to make sure that they're balanced out. First off, iron 3 oxide is actually 69.9% iron and 30.1% oxygen, but iron 2 oxide is 77.7% iron and 22.3% oxygen.
The percentage composition of a compound is the percentage by mass of each element in that compound. Iron, for example, forms two binary compounds with oxygen. The percentage composition of one is 30.1% oxygen and 69.9% iron. The percentage composition of the other is 22.3% oxygen and 77.7% iron. Because of their differing percent composition, their properties differ. To find the percent composition, divide the mass of a given element in a sample of a compound by the total mass of the sample and multiply by 100. The percentage composition can be used to find the empirical formula of an unknown compound. For example, we discover that an unknown compound is 69.9% iron by mass and 30.1% oxygen. If we took a 100-gram sample of this compound, 69.9 grams of it would be iron and 30.1 grams would be oxygen. We can convert this to moles and divide both by the smaller number of moles. This gives us the relative proportions in moles. To find the simplest whole number ratio, we multiply by 2. The empirical formula for this iron compound is Fe2O3.
So this process right here, I want to point out to you how simple this really is. Now, you might not know where these numbers are coming from yet because you haven't done one of these, but you will, and it will make so much sense if you force yourself to slow down and think about each step. We're converting from grams of iron into moles of iron to see that it's 1.25 moles of iron. We convert from grams of oxygen into moles of oxygen to see that it's 1.88 moles of oxygen. The next step really confuses students, and I'm not exactly sure why, because all we do in this step is out of the 1.25 moles and the 1.88 moles, we simply choose the smallest number of moles. Now, because we know what numbers are, we know that 1.25 is smaller than 1.88. And because it's a smaller number, we divide both of those numbers by 1.25. 1.25 divided by 1 is 1. That's why we have 1 mole of iron. 1.88 divided by 1.25 is 1.5. And that is the ratio at which iron occurs with oxygen in this type of iron oxide. Now, you can't have 1.5 of an oxygen atom, and so we have to make these a whole number, and so we simply multiply it by 2 to give us that whole number. So Fe2O3. Again, graphical representation of this process. Please use this. You can dissect this. You can have this out while you're working your sample problems, while you're working prep problems, and while you're working the problems on the worksheet, but please use these graphical organizers. All right, let's work a sample problem here. Let's find the percentage composition of copper 1 sulfide. That's the formula here is going to be copper 2S, Cu2S. So we know what the formula is. What we're trying to find is the percent composition of the Cu2S. So what we're going to do, we're going to go from the formula to the molar mass, right? We're going to use the formula to figure out the molar mass. And once we have the molar mass, we're going to find the mass percent of each element. So we know that there are 2 coppers and 1 sulfur, so we use the molar mass of each of those to calculate the molar mass of copper 1 sulfide as being 159.2 grams. So now that we have that, we can take the mass of the copper, divide that by the mass of the total sample, multiply it by 100, and we get ourselves a percentage. Turns out that it's 79.85% copper. Next, we take the mass of the sulfur, which again we calculated on the last slide. We divide that again by the mass of the whole sample, multiply by 100, and we get 20.15% sulfur. Easy peasy lemon squeezy. All right, chemistry, I will see you next period.